Piping vibration, fundamental concepts and impact on industrial systems. Overview, Introduction to vibration. Vibration-induced fatigue failures in process pipework are a significant concern for industries such as oil, gas, and chemical processing. These failures can lead to catastrophic consequences, including sudden release of hazardous or flammable fluids, which pose severe safety risks to personnel and the environment. Additionally, such failures often result in costly production downtime and expensive corrective actions, further impacting operational efficiency and profitability. Traditionally, piping systems have been designed using static analysis methods, with minimal consideration for dynamic effects like vibration. This oversight stems from the fact that most piping design codes do not adequately address vibration-related issues, leaving operators to manage these problems reactively rather than proactively. Recent trends have exacerbated the problem. Increased flow rates due to debottlenecking and relaxation of erosion velocity limits have led to higher fluid velocities, which in turn generate greater turbulent energy within process systems. Furthermore, the adoption of thin-walled piping materials, such as duplex stainless steel alloys, has made systems more flexible and susceptible to stress concentrations, particularly at small bore connections. Industry data underscores the seriousness of this issue. For example, in the UK offshore sector, vibration-induced fatigue accounts for over 20% of all hydrocarbon releases. Similar patterns are observed in onshore facilities, where 10 to 15% of pipework failures are attributed to vibration. These statistics highlight the urgent need for comprehensive guidelines and proactive strategies to mitigate vibration risks throughout the lifecycle of process piping systems. Vibration is defined as an oscillatory motion about an equilibrium position, and it can occur in any structural system, including piping networks. A simple analogy is a mass spring system. When displaced and released, the mass oscillates at its natural frequency, which is determined by the system's mass and stiffness. In piping systems, natural frequencies are influenced by factors such as pipe diameter, wall thickness, material properties, fluid density, and the arrangement of supports and valves. Each natural frequency corresponds to a unique mode shape, characterized by nodes, points of zero motion, and antinodes, points of maximum motion. Vibration can be quantified using displacement, velocity, and acceleration, with velocity being the most relevant parameter for assessing dynamic stress and fatigue risk. Displacement tends to dominate at low frequencies, while acceleration becomes significant at high frequencies. Velocity provides a balanced measure across the spectrum. Excitation sources can be tonal, where energy is concentrated at discrete frequencies, or broadband, where energy spans a wide frequency range. Resonance occurs when the excitation frequency matches a natural frequency, leading to amplified vibration levels and increased risk of fatigue failure. Forced vibration, on the other hand, occurs when excitation frequencies differ from natural frequencies, resulting in lower but still potentially harmful vibration levels. Understanding these principles is essential for diagnosing vibration issues and implementing effective mitigation strategies. Flow-induced turbulence and mechanical excitation, pulsation, acoustic excitation, and transient effects. Flow-induced turbulence is one of the most prevalent causes of piping vibration. It arises from irregularities in fluid flow, particularly at points of discontinuity such as valves, bends, tees, and reducers. These features disrupt the flow pattern, generating turbulent eddies and broadband kinetic energy that excite low-frequency vibration modes in the pipework. The severity of turbulence-induced vibration depends on factors like fluid velocity, density, and system geometry. Mechanical excitation is another significant contributor, typically associated with reciprocating or positive displacement pumps and compressors. These machines impose dynamic forces on connected piping systems, either directly through suction and discharge lines or indirectly via structural transmission through shared supports. The excitation frequencies often correspond to the machine's operating speed and its harmonics, creating multiple opportunities for resonance with the piping's natural frequencies. When such coupling occurs, vibration levels can escalate dramatically, leading to fatigue failures at critical locations such as welds and small bore connections. Preventive measures include careful design of support arrangements, isolation of vibration sources, and operational adjustments to avoid coincident frequencies. Pulsation refers to dynamic pressure fluctuations within the fluid, which can amplify through acoustic resonance in the piping system. Reciprocating compressors and pumps are common sources of pulsation, generating oscillatory pressure waves that interact with the system's acoustic natural frequencies. When these frequencies align with structural natural frequencies, severe vibration can occur. Rotating stall and centrifugal compressors is another mechanism that produces tonal pressure pulsations, particularly under low-flow conditions. High-frequency acoustic excitation, often associated with control valves, relief valves, and orifice plates, poses a unique challenge due to its ability to induce rapid fatigue failures in thin-walled pipes and small-bore connections. These failures can occur within hours of exposure to high-frequency vibration. Transient phenomena such as surge, water hammer, cavitation, and flashing also contribute to vibration problems. Surge results from sudden changes in fluid momentum during rapid valve operations, generating pressure waves that propagate through the system. Cavitation and flashing involve phase changes in the fluid, creating localized forces and noise that exacerbate vibration. Effective mitigation requires a combination of design improvements, operational controls, and, in some cases, specialized damping devices. Fatigue and structural damage, operational and safety implications. Vibration-induced fatigue is a critical integrity threat in process piping systems. Dynamic stresses generated by oscillatory motion can initiate and propagate cracks at stress concentration points, such as weld toes and small-bore connections. Once a crack forms, it can grow rapidly under cyclic loading, eventually leading to through-wall failure and fluid leakage. In severe cases, catastrophic rupture may occur, posing significant safety and environmental hazards. The fatigue life of a component depends on factors such as vibration amplitude, frequency, material properties, and the presence of corrosive or erosive conditions. Intermittent vibration can extend fatigue life compared to continuous exposure. But the risk remains substantial. In addition to fatigue, vibration can cause fretting, a wear mechanism that occurs when two surfaces in contact experience cyclic relative motion. Fretting leads to material loss, surface degradation, and potential loss of containment. These issues underscore the importance of proactive inspection, monitoring, and maintenance strategies to detect early signs of damage and implement corrective actions before failures occur. The consequences of vibration-related failures extend beyond mechanical damage. Safety risks include the release of hazardous or flammable fluids, which can lead to fires, explosions, and environmental contamination. From an operational perspective, unplanned shutdowns due to vibration-induced failures result in significant production losses and increased maintenance costs. Regulatory compliance may also be compromised, exposing operators to legal and financial liabilities. Furthermore, vibration issues can erode stakeholder confidence and damage corporate reputation. Addressing these challenges requires a holistic approach that integrates design best practices, risk assessment methodologies, and continuous monitoring. Techniques such as vibration measurement, dynamic strain analysis, and predictive modeling can help identify high-risk areas and guide the implementation of effective mitigation measures. Ultimately, fostering a culture of proactive management and adherence to industry guidelines is essential for ensuring the long-term reliability and safety of process piping systems.